Since its launch, the James Webb Space Telescope, JWST, often heralded as the Hubble Space Telescope's replacement, has revolutionized our understanding of the cosmos. The telescope has given us a unique view on the universe, exposing mysteries and locating locations that were unknown to science. Thanks to the state-of-the-art equipment of the JWST, scientists can now see into the deepest regions of space and study planetary systems, stars, and galaxies that were formed billions of years ago. This article explores the many facets of the JWST, covering how it has changed our perception of the universe and its mechanical marvels and historic discoveries. Understanding the 1990 launched Hubble Space Telescope, the JWST's precursor, is crucial to understanding its significance. The Hubble Space Telescope allowed scientists to see stars, nebulae, and galaxies in the distance without being obstructed by Earth's atmosphere. From measuring the pace of the universe's expansion to seeing the collision of comet Shoemaker-Levy 9 with Jupiter, Hubble has made enormous contributions to science. Through its deep field pictures, which capture light from billions of light-years away galaxies, we have been able to see into the early universe. Nevertheless, despite its achievements, Hubble had several drawbacks. Its sensors were made for the ultraviolet, visible, and near-infrared regions of the spectrum, and its 2.4-meter-wide primary mirror limited its capacity to gather light. The need for a new telescope emerged when astronomers pushed the limits of human knowledge. This telescope had to be able to see in the infrared spectrum in order to look through clouds of cosmic dust and observe the universe's first galaxies. Before Hubble had realized its full potential, in the mid-1990s, the idea for the James Webb Space Telescope started to take shape. The James Webb Space Telescope, JWST, was intended to be the next great observatory, a telescope that would gaze farther back in time than Hubble and gather light from the first stars and galaxies that formed after the Big Bang. The telescope was named in honor of James E. Webb, NASA's administrator during the Apollo era. There were many engineering difficulties in the JWST's design. In contrast to Hubble, which circles the planet at a height of roughly 570 kilometers, the JWST would be situated at the second Lagrange point, L2, which is approximately 1.5 million kilometers away from the planet. Although this position provides a stable atmosphere with little interference from Earth's heat and light, it also means that astronauts are unable to maintain or repair the telescope. A significantly larger mirror than Hubble's was needed for the JWST in order to observe faint, distant objects. The solution was a segmented mirror with a total diameter of 6.5 meters, composed of 18 hexagon-shaped, gold-coated segments. This mirror was only able to unfold after the telescope arrived at its destination. It had to be folded in order to fit inside the Ariane 5 rocket. In order to maintain the instruments of the JWST a few degrees above absolute zero, heat and light from the Sun, Earth, and Moon had to be blocked by a sun shield. The 5 layers of the sun shield, which is the size of a tennis court, are composed of a unique material called captivated that is resistant to high temperatures. In the end, on December 25, 2021, the JWST was ultimately launched following years of planning, setbacks, and cost errors. Researchers and space enthusiasts from all over the world witnessed the historic launch. After the telescope was sent into orbit by the Ariane 5 rocket, the JWST began a convoluted, painstakingly organized series of operations that lasted over 30 days. The solar screen on the telescope was the first significant component to deploy, requiring thousands of elements to work in unison across multiple systems. The mission may have been in jeopardy with any failure at this point. Following the successful deployment of the solar screen, the mirror segments started to unfold and align. Because each section needed to be positioned with nanoscale accuracy, this process took several months. After completing its deployment and calibration, the JWST's instruments were prepared to start gathering data in the middle of 2022. The telescope's capacity to see in the infrared light showed the universe in a new light, with astounding clarity and detail. The initial photos that were made public were nothing short of spectacular. Observing the first galaxies to develop after the Big Bang billions of years ago is one of the main objectives of the JWST. These galaxies are so far away that redshift, or the stretching of light into the infrared spectrum, is a result of the universe's expansion. Although Hubble was able to identify these far-off objects, The JWST's infrared capabilities enabled it to observe them with remarkable clarity. During the first year of its mission, the JWST produced a number of unique discoveries. The discovery of galaxies that existed just a few 100 million years after the Big Bang was one of the most important. These galaxies challenged accepted theories of galaxy creation and development by seeming larger and more evolved than previously believed. Although the JWST's data imply that certain galaxies started far more quickly and expanded larger sooner than anticipated, scientists had long thought that the early galaxies were tiny and grew gradually over time by merging with other galaxies. This discovery has forced cosmologists to re-evaluate existing theories about the creation and development of galaxies. Massive, hitherto unseen structures were also photographed by the JWST. The telescope, for instance, studied the minute intricacies of the cosmic web, a massive web of filaments that links galaxies throughout the universe. These filaments, composed of gas and dark matter, act as the framework for the formation and evolution of galaxies. New information about the large-scale structure of the universe and the influence of dark matter on its formation has been made possible by the JWST's observations of the cosmic web. In addition, the JWST has completely changed the way we think about how stars develop and evolve. Because vast clouds of gas and dust obscure visible light when stars form, the JWST is able to examine the formation of stars in unprecedented detail because of the ability of infrared light to pass through these clouds. Approximately 1,344 light-years away from Earth, the Orion Nebula is a stellar nursery and one of the telescope's initial objectives. Many young stars, some still immersed in their birth clouds, were visible in the JWST's photos. These observations have yielded fresh understandings of the mechanisms leading to the development of planetary systems and the formation and evolution of stars. The last phases of star evolution have also been studied by the JWST, yielding breathtaking pictures of dying stars and the nebulae they produce. The processes that control a star's demise, such as the creation of white dwarfs, neutron stars, and black holes, have been clarified by these findings. The JWST mission's capacity to investigate exoplanets, planets that orbit stars outside of our solar system, is among its most intriguing features. By examining the atmospheres of these far-off worlds, the telescope's instruments can look for indications of habitability and potentially even life. The JWST made a number of significant exoplanet-related discoveries during its first year of operation. The discovery of LHS 475b, an exoplanet roughly 41 light-years from Earth, was one of the most noteworthy. This planet, which is around Earth's size, takes just 2 days to complete its orbit around its star. The dense atmosphere of LHS 475b, which may be made of carbon dioxide, methane, or water vapor, was discovered by the JWST. Other exoplanets with varying atmospheric conditions have also been spotted by JWST. Some of these planets have clean atmospheres dominated by hydrogen and helium, while others have thick, hazy atmospheres rich in methane and other hydrocarbons. The diversity of planetary systems and the circumstances that might support life have been better understood thanks to these observations. Whether life exists elsewhere in the universe is one of the most fascinating problems in cosmology. The JWST can look for biosignatures, or chemical indicators that could point to the presence of life, even if it cannot directly detect life. For instance, the presence of life processes may be indicated by the finding of oxygen or methane in the atmosphere of an exoplanet. A new chapter in the hunt for extraterrestrial life has begun thanks to the JWST's capacity to investigate exoplanets. The telescope will provide vital information as it observes more planets, which may help put an end to the perennial question of whether or not humans are the only people in the cosmos. Apart from studying far-off galaxies and exoplanets, the JWST has taken pictures of some of the universe's most exquisite and enigmatic objects. Among the most remarkable is the Tarantula Nebula, a large star-forming area found in the Milky Way's satellite galaxy, the Large Magellanic Cloud. Thousands of new stars are being formed in the Tarantula, also known as 30 Doradus, which is a massive area of gas and dust. JWST photos of this region show complex gas filaments, bright young star clusters, and supernova explosion remains. New understanding of the mechanisms behind star formation and the life cycles of large stars has been made possible by these observations. Even though the JWST has significantly advanced our understanding of the cosmos, there have been difficulties and disagreements along the way. The telescope's final cost came close to $10 billion, much more than the original estimate due to several delays and cost overruns during its development. These problems spurred discussions about the project's worth and viability among scientists and policymakers. While some detractors said that money better spent on other scientific projects should have gone toward the JWST, others maintained that the telescope's potential for groundbreaking discoveries made it worth the cost. The goal of the James Webb Space Telescope is an international, cross-generational human achievement as much as a scientific undertaking. Although its findings are already changing textbooks and deepening our understanding of the cosmos, the entire effect will become apparent over the next several decades. Future generations will be motivated to reach for the stars as the JWST pushes the limits of human knowledge and makes even more significant discoveries as it continues to explore the cosmos. The fresh questions JWST asks about the universe, in addition to its state-of-the-art equipment, make it a tremendous leap forward in the science of cosmology. The JWST is positioned to advance our comprehension of cosmic events in previously unattainable ways as it continues its mission. Capturing light from even the most distant galaxies allows it to investigate the early cosmos, which is one of its most fascinating features. Understanding the evolution and development of the cosmos depends on these early galaxies. Scientists can learn more about the formation, growth, and merging processes of galaxies in the early phases of the cosmos by monitoring them. Astronomers may examine these far-off objects in detail thanks to the JWST's capacity to detect faint infrared emissions from them, which sheds light on the events that created the cosmos soon after the Big Bang. Furthermore, supermassive black holes, mysterious objects thought to exist in the centers of most galaxies, including our own Milky Way, are studied with great help from the JWST, including their growth and evolution. The development and evolution of galaxies depend heavily on our ability to comprehend how these black holes developed and expanded. Dark matter research is one of the JWST's other main areas of interest. Dark matter is invisible and only discernible by its gravitational effects. It makes up around 27% of the mass and energy of the universe. Dark matter does not emit light or energy. Through the mapping of dark matter distribution in large-scale cosmic structures and galaxy clusters, the JWST contributes significantly to our understanding of the nature and function of dark matter in the universe. Beyond just identifying their existence, exoplanets can be thoroughly analyzed in terms of their atmospheric makeup thanks to the capabilities of the JWST. Scientists can determine the chemical composition of an exoplanet's atmosphere by analyzing the light that travels through it while it orbits its parent star. This method, called transmission spectroscopy, is useful for locating possible biosignatures, including water vapor, methane, or oxygen. These findings are essential for determining if exoplanets are habitable and for comprehending the circumstances that might be favorable to life. The capabilities of the telescope also include the research of planetary system distribution and origins. Protoplanetary disks are areas around young stars where planets are formed, and they are visible to the JWST. Astronomers can get more knowledge about the mechanisms leading to planet formation and the variables influencing the evolution of planetary systems by closely examining these disks. This study offers insightful background information for comprehending the creation and development of our own solar system. The JWST also advances our understanding of star populations and their evolution. The JWST provides valuable insights into the formation, evolution, and demise of different types of stars by monitoring star clusters at different phases of their life cycle. These observations provide information about nucleosynthesis, the process by which stars create new elements, and the contribution of supernovae to the enrichment of the interstellar medium. The material that resides in the space between stars, known as the interstellar medium, is another important subject of research for telescopes. This medium, which is made up of gas, dust, and cosmic rays, is essential to the universe's matter cycle. The JWST contributes to scientific understanding of the formation and evolution of stars and planetary systems, as well as the distribution of elements required for life throughout the universe, by examining the structure and distribution of the interstellar medium. Apart from its scientific endeavors, the JWST has significantly influenced technology and engineering fields. Improvements in precision engineering, optics, and material science were necessary for the development of the telescope. For instance, new materials technologies were used to create the telescope's segmented mirror and sunshield, which were designed to resist the extremes of space travel. Beyond astronomy, the technology created for the JWST has implications for industries including robotics, telecommunications, and remote sensing. Additionally, international cooperation in space science is being improved with the JWST project, jointly undertaken by NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. The JWST is an example of a cooperative project that combines the resources and experience of several nations. The ability of the international scientific community to study and comprehend the cosmos is strengthened by this alliance, which promotes collaboration and knowledge exchange. The observations made by the telescope also have wider cultural and educational effects. A new generation of scientists and engineers have been inspired by the JWST's amazing photos and discoveries, which have captured the public's imagination. The JWST inspires young people to pursue careers in science and technology by involving the public with its discoveries and fostering interest in these subjects. It is inevitable that when the JWST carries out its mission, it will uncover novel occurrences and refute accepted beliefs. By pushing the limits of human knowledge and broadening our perspective of the cosmos, its observations will continue to improve our understanding of the universe. Fundamental concerns concerning the universe's beginnings, the nature of dark matter and dark energy, and the possibility of extraterrestrial life will be addressed by the JWST's discoveries. To sum up, the James Webb Space Telescope is a revolutionary advancement in our understanding of the cosmos. Our knowledge of astronomical phenomena is changing as a result of its sophisticated technology and capabilities, which span from the study of exoplanets and the interstellar medium to the development of galaxies and black holes. Beyond astronomy, the JWST has impacted technology, international collaboration, and public science engagement. The JWST will uncover fresh information as it explores the cosmos and encourage upcoming generations to aim for the heavens.